graduation, he's planning to pursue a PhD in theoretical cosmology and work at the interface between theoretical physics and modern cosmology. And today, he'll be presenting a talk on cosmological constraints on exotic neutrinos. Mr. Lachlan Lancaster.
Did we want to get the other?
No, for you it won't be ready on time.
Yours. Okay.
Come on.
So we just have one slide, but yeah. So thank you for the introduction, Dorothy. So today, as Dorothy mentioned, I'm going to be talking to you guys about basically the work that I did this summer, which was at UC Davis under Dr. Lloyd Knox. Basically using the cosmic microwave background radiation, which I'm sure you guys have probably heard a lot about in these colloquium talks, but I'm kind of going to go over a little bit. Using this to constrain neutrinos, which, as you also have probably heard a lot about, are some particles that we don't know very much about, and they're very hard to kind of learn anything about because they're so neutral, they don't interact via the electromagnetic force. They're weakly interacting, and they're not very massive. But they are massive, and that's kind of a problem. Anyway, so we're going to start where most starts talk, in the beginning, when the universe was created. It's made a lot of people very angry and was generally regarded as a bad idea, as said by Douglas. No, that was just one of my favorite quotes. So most people generally think of the beginning of the universe looks something like this, some really big explosion. I like the picture here because it kind of gives you an idea of why Hubble found that the universe was expanding. You see that things that are farther away from the center of this big explosion are moving faster than things that are closer. But maybe you can't see that because the picture isn't moving. But you can imagine that because they got out here faster than the things that are there, they are moving faster than the things that are closer. So that's nice, but this isn't really what the beginning of the universe looked like. The beginning of the universe looked a lot more like this, which is kind of a rather boring picture, but it's true. I mean, and it's kind of weird to even associate a color to this because the universe was so dense and so hot that you can't really associate a color to, I mean, our visual perception of color doesn't really make any sense in the temperature that we're talking about here. But the beginning of the universe was basically very homogeneous, very isotropic. It looked the same in every direction. It was pretty much the same wherever you were, except for these very, very small perturbations to that homogeneity and isotropy. So perturbations on the order of like these little differences in the lines that you can see here, which I didn't put there. It's just something that came out of PowerPoint. But that's how small the differences are. So to start with kind of the big picture of cosmology, in cosmology we're kind of dealing with very, very large scale. So to talk about the big picture of cosmology, this is the biggest picture that you can have, the biggest picture that mankind has ever taken. This is a representation of the temperature anisotropies in the cosmic microwave background radiation from the Planck satellite. I'm sure everybody here has probably seen this picture a million times. To give you an idea, I mean, this distance doesn't really make sense, but if you want to associate a distance to where this picture is being taken from, it's kind of about 13 billion light years away, right? So it's a pretty big picture. It's light that's traveling to us from the very beginning of the universe, when the universe was so dense and so isotropic and homogeneous, and after it expands a little bit, finally this light that's been interacting with itself for so long gets to free stream out, and eventually it comes to us, about 13 billion years later. Some of it just has been traveling for 13 billion years and then bounces off an air molecule in the atmosphere, and then we never see it, so that's kind of sad. But yeah, so I want to talk about why this is kind of a good place to look at neutrinos. Neutrinos, as I mentioned earlier, they're weakly interacting. It's kind of hard to see their effects anywhere else. As I'll talk about later, the only way that we were able to study them on Earth is with these huge, massive detectors. But in cosmology, you kind of are able to get around that because you've got such a big lab to look at. If you don't have very much control over the lab, but it's so large that you can, even the slightest change of the slightest small thing can make a big difference on the largest of scales. So this is a good part about this. This is the ratio of the number of neutrinos to the number of baryons in the universe is about about 1 billion. So that's very nice because there's so many neutrinos, even though they're so small, they can have a large impact on the rest of the universe, right? So even a very, very small change in how these neutrinos interact with each other can make a noticeable difference in something like this, the anisotropies and the temperature of the microwave background. So why do we care to look at neutrinos in the first place? So neutrinos, as you guys might have heard, if anybody went to the talk on the Nobel Prizes this year, neutrinos have mass, as we recently found out. This picture here is of a few guys. These are 2 guys in a boat cleaning the inside of the Super Kamiokanda detector in Japan. This is one of those giant detectors I was talking about. And the head of this program is one of the people that won the Nobel Prize this year for basically saying neutrinos have mass. So this is a problem, kind of, because this is right here is the full standard model Lagrangian. And as you can see upon easy inspection, easily looking at this, you can see that neutrinos don't have mass. So that's a problem because they do, as we found. So we kind of have to fix this problem. Clearly, this isn't correct. If these guys are telling us that neutrinos have mass, and this clearly says that it doesn't. So we have to kind of add on some more terms to that. So that was the whole standard model Lagrangian, and then you say, okay, I want to add on some more terms to explain neutrino mass. So up here is kind of, at the top is kind of one of the more general types of Lagrangians that you can start with. So it basically includes these, on the left is a scalar interaction term, and on the right is a pseudo-scalar interaction term. Doesn't really matter. Basically just, you've got these general types of interactions, and in order to talk about it, I mean, right now it's a very starting approach, right? People haven't really looked into this that much, so you want to simplify the model as much as you can. So basically you move to what's at the bottom, which is basically, let's ignore everything that's the pseudo-scalar stuff, whatever, throw that away, and then we'll basically assume that this interaction doesn't depend on what type of neutrino you're dealing with. So basically, you see at the top it's Gij, that's talking about the different electron or muon or tau neutrinos, and then saying, okay, let's just say they all interact the same way with each other. And then we basically have just reduced this interaction to neutrinos interacting with each other via this particle phi, which is a scalar boson. Has people have heard of scalar bosons before? Probably. Have anybody heard of the Higgs field? Yeah, that's a very, very popular scalar boson. So these things have come up recently, so they're not kind of crazy. Maybe several years ago they would have been thought as more crazy. But anyway, so we want to simplify this, and then you kind of draw out these types of interactions. It's a lot of field theory and stuff that I won't go into. And basically, you want to take this interaction and then you want to simplify it into a cosmological sense, something you can talk about in terms of cosmology. So to do that, you kind of need to specify what cosmology you're working in. These are, people may or may not have heard of metrics. Basically, this is a way of telling the distance between two things. In general relativity, this is the basis of everything. This is how you tell the curvature of space and time and kind of relate things. So when you're talking about cosmology, you need to work in the context of general relativity because this is the law. This is the set of laws that kind of govern things on large scales. So the top thing is the Minkowski metric. Talks about basically that's all of special relativity right there. The thing in the middle is the FRW metric, which basically just talks about general relativity in the context of cosmology, but it assumes that everything is the same in every direction and everything is the same wherever you are. It's homogeneous and isotropic. And this is pretty much true, as you saw from what I was talking about at the beginning, but it's not really true, as you can see from looking at the anisotropies in the microwave background, right? It's a little bit different. It's not exactly the same everywhere you look. So in order to kind of get at trying to understand those anisotropies, you need to change the FRW metric a little bit. And you can do that in a bunch of different ways. One of the ways you can do that is what I have here, which is just another metric. Formally, it's called the conformal Newtonian gauge, but it's basically just a way of taking the FRW metric and saying, let's just change it a little bit. Let's add on little perturbations to that. And then you use this in the context of general relativity and come through a bunch of different equations. So again, I'm justifying basically, we're allowed to work in perturbation theory where we just want to take little tiny changes, anything of non-linear order. So if we get a square of two small quantities, these quantities are on the order of 10 to the minus 6. So anything that's squared is like really, really small. We don't really care about it. So it's very nice to deal with just very linear terms. So I'm going to very, very quickly go through a bunch of the equations that lead into deriving how these neutrinos evolve. And I mean very, very quickly because it's not really something that you're going to be able to understand in the amount of time I have to talk, unless you're super processor brain. But anyway, so this is basically, you start with the general relativistic form of the Boltzmann equation, which tells you how interacting particles evolve in phase space. Okay, so this basically says the time derivative of the phase space distribution of a particle is equal to this collisional integral, the C of f, of the, which basically, the C depends on how these particles interact with each other, and the L depends on how they would interact with each other if this collision wasn't happening. And then that expands out into this is the whole general relativity stuff, and then basically you have to look at the left-hand side, get an idea for what the phase space distribution of these neutrinos would look like. This is kind of like a perturbation to the Maxwell-Boltzmann distribution. Again, I'm just going to go through this very quickly, so don't feel like you're missing out on anything. Basically, you take this and you plug it into, you take that distribution, you plug it into the equation there, simplify because you're a physicist, you take a Fourier transform, and then you have to worry about the silly collision integral that's there. That gets a lot more complicated, and that's where you have the model coming in. It's pretty terrible, but eventually you can do some more perturbation theory. You get this giant expansion, which is finally something that you can work with, and basically you get down to this simplified version where everything, all of your model, at least in terms of this massive scalar boson, is dependent on this effective coupling constant. So this is something we can finally work with, of course, using the wonderful use of our favorite tool, mathematics. So once you're finished with all this, what you finally end up with is this Boltzmann hierarchy, which you can plug into code to compare with the cosmic microwave background. The only thing that the model that I was talking about changes is this. Everything, without my model, everything is the same except for this term. Take that term away and it's exactly what neutrinos are in the standard model. So that's kind of strange to think one term is not going to change a whole lot. But neutrinos make up a large portion of the universe, so it actually does. So I basically take this, I plug it into a code called, I basically have to modify a code called CAM, which is basically a lot of learning Fortran and learning where the right things have to go. But if you like to code, it's a fun thing to do. And you take this code CAM takes these cosmological parameters. Has anybody seen these before? Okay, Alex has seen these before. And Jeremy. Okay. So these basically are a few of these parameters that we don't really have good theories for. Well, yeah, we don't have exact theories for what these should be. So we basically take these parameters and let them take a bunch of different values and then compare what the code CAM gives us as a prediction for these, gives us as a prediction for the power spectrum of the microwave background and compare it to the actual data that we have. So as you can see, the first 6 are things that are usually taken into an analysis, and the last one is for this model event. So we take those parameters and we plug it into CAM. It gives us this nice power spectrum for the temperature anisotropy. I'm not going to go into what a power spectrum is, but it takes a little bit more time. Then we take this nice, beautiful picture. We use a code called HealPix. That basically gives us these data points, right? And then we want to have a way of comparing these cosmological parameters with this fuzzy picture of dots. So we have to use a program called, well, there are several different choices here. We basically use a Bayesian inference algorithm to kind of pick a bunch of different values of those parameters and compare them with the data, and then continually pick better and better parameters until you have best fit models for comparison. So after running for a bunch of times, you get these different lines here comparing to the data, and you see some fit well, some don't. And yeah, so you finally get that picture. To give you an idea of what that, to give you an idea of what that kind of looks like, this is a kind of, so there are 7 dimensions in this parameter system, in this Bayesian analysis, but I'm just portraying 3 parameters here, and then the color is representing the strength of the neutrino interactions in my picture. Okay, so you can kind of see how the program is going to evolve these points to higher and higher likelihood. And I'm going to skip through it a little bit. You can see you're getting this delineation between the red is strongly interacting neutrinos and the blue is weakly interacting neutrinos. You see we develop this multimodal distribution towards the end where we've got a strongly interacting mode, a weakly interacting mode. So this is interesting because the weakly interacting mode is the standard cosmological model. The strongly interacting mode is not something that you expect to see because neutrinos, at least you would expect, don't interact through this very simplified model that we've come up with. So this is strange. Previous results had basically, so this is after you run that model, that inference algorithm for a long enough time, you have basically a posterior, a bunch of points left over at the end. And that gives you basically a probability distribution on the parameters that you have. So this is some previous results for that marginalized distribution. Basically, what is that distribution just as a function of that one parameter? So this is some previous results of people who had looked at this same model. And they found that you have this strongly interacting mode. And past this point, you basically can't tell the difference. This is all the standard model of cosmology. So past that strength, everything looks the same. But once you get up to this, you've got this peak in the posterior distribution. Obviously, it's not very well favored compared to the other stuff. You can see it doesn't look very likely, but it's still there. So basically, what my project was working on was updating this. So I used more recent data and a different analysis method to basically do this better. And what I end up with is this. You can see that in this model, the strength of the interaction is actually even stronger. So this is a log scale, right? So you can see these are kind of centered around -2. whereas this is more centered around minus 1.7, so that's stronger interaction. T effective is bigger. And so this isn't what we really wanted to do. At the beginning of the summer, my research advisor told me, okay, our goal for the summer is to make this go away. And when I brought this back to him, he was kind of disappointed. So we said, okay, well, what are the differences between this mode and that mode? And that's kind of the game you want to play in this cosmological parameter estimation. You want to look at this mode and say, how can we rule this out? How is this different than that one? And the biggest difference, believe it or not, comes up in the matter power spectrum, another power spectrum basically for these cosmological data. This is kind of the biggest difference in all the data sets that you can look at. You can see that the red is the interacting mode, the black is the standard lambda CDM. You can see it doesn't really look like too much of a difference. Strangely, when you add in data from that, you get this. So BAO is baryonic acoustic oscillations, it's basically a measure of that matter power spectrum. And you can see that this mode is completely wiped out, almost gone. So that's nice. It means that with this new data, you can actually rule out this strongly interacting mode for neutrinos. It's kind of nice and not nice. It's nice because we rule out this possibility. It's not nice because it would be kind of cool to have discovered these strongly interacting neutrinos. So what does this mean for the future? Basically, there are a lot of possibilities to push this back. So the Fermi interaction for weakly interacting neutrinos is actually like way back here. So there are a bunch of possibilities in between where you could still have interactions between neutrinos that are relatively high in strength. But it's not really something that's going to be constrained by cosmological parameters in the near future. We did a Fisher matrix analysis, which is basically just a way of predicting how this is going to push things back in the future. And it doesn't show many promising results. You can also do MCMC analysis, which is basically just a different type of inference than what I was using. So when I first made this, we hadn't completely wiped out this mode. So we said, well, if we get the constraints that we think we're going to get with the further cosmological data, this mode will look like this, and we'll be even more confident in these strongly interacting neutrinos. Clearly, that's not the case because with this new data, that's completely gone. But even in the future with more data, we only think that this is going to be pushed back like a very little amount compared to what it used to be is just around here. So basically our idea is that we can't push back these interactions very much further than we have already. But yeah, so what I want to basically give you the idea of is what working in the realm of cosmological parameter estimation is like. Basically, it's a lot of doing math to figure out how things are going to evolve, converting that math to code because you're not going to write out all of the comparisons between data and models by yourself. And then kind of a lot of, I think that the creativity part comes in figuring out what data you want to use to compare these different models. And also in the mathematics, some of the mathematics gets quite difficult, and you have to come up with a few interesting ways of getting around that. So if you're into coding and math, which a lot of people aren't, but a lot of people also are, then this might be an interesting thing for you. So I'd like to thank the people that I worked with in my group, and Dr. Francis Young, who did the previous work on this, was very big in helping me on this as well. Thanks.
Anyone has a quick question?
Yeah.
Let's get set up.
Anyone has a quick question?
No question.
I have a question. I have many, but I will ask only one. when you say strong, it's in the realm of, still within the realm of weak. You are, have the interaction is that the neutrinos of the same kind, if I understood it right. Right? So, how does it compare to, say, the strength of G, the standard neutrino, in standard weakling class?
So when I'm saying strong, what am I comparing?
Just order of magnitude.
Yeah, so it's about the strongly interacting mode that I had there was about 10 to the 9 orders of, well, so 9 orders of magnitude above the Fermi. Yeah. So
That's very strong.
yes, exactly. So it's very strong. And what the cosmological data tells us is we're not actually able to push it below maybe 5 orders of magnitude stronger than the Fermi interaction. So unfortunately, even though neutrinos are, as I'm saying, such a good place to look for these interactions, you can't really push it too far.